Last video I stopped at extending intrinsic semiconductors limitations. Okay, so the limitations, as you know, okay, let's go back to the limitations once. So limitations, as you know, that the conductivity is less compared to conductors, a good conductors, and it's a temperature dependence. To overcome these two, you what you do is like you add few impurities. So these impurities will give you the carriers. Okay, and also this will, if the carriers are already available, the conductivity will be better than the intrinsic semiconductor, and also it will be independent of temperature. Okay, it will be independent of temperature. It will more depend on the applied voltage than temperature. So that is two advantages you are going to get from the extrinsic semiconductor by doping uh, impurities in the intrinsic semiconductors. This is, we are doping, that's why it's called dopant. There can be two types. If you add group 4 or pentavalent impurities, you get n-type semiconductor. They are like aluminum, boron, gallium, etc. If you add trivalent impurity, so it leaves one vacant space. That's why you get p-type semiconductors, phosphorus, uh, antimony, and all those things, arsenic and antimony. You are getting it. Now, how much doping you do? Doping is typically of the order of 10 to the power 20 to 20 to the power 27 atoms per meter cube. Okay, you have to take a 1 meter by 1 meter block, so this will be nearly few thousands of kilos. How much you are adding? This is nearly Avogadro number, so it will be like few grams. In thousands of kilos, you are adding only few grams of your impurities. So that is that much less impurities you are going to add, and this is the number of atoms you are adding. That many number of carrier concentrations you are going to get additional to the intrinsic semiconductor. Okay, they will be readily available for you. Now let's discuss about the n-type semiconductor. N-type semiconductor, you add as a phosphorus atom, you have added some phosphorus atom you have added, so it has an energy level which is very close to your conduction band. Okay, very close to conduction band. So this is the energy difference compared to the total energy difference of your semiconductor. Because this is a small gap, the electron can jump from here to here. When electron jump from phosphor atom, it becomes phosphorus ion, or the dopant ion it becomes. Because pentavalents are neutral, even trivalent are neutral. When they leave, one electron is left, it becomes positively charged ion. If you observe here carefully, let's go back. If you observe here carefully, so what you are going to find is your electrons are here, but holes are not formed. Unlike your intrinsic semiconductor, if the electron is here, there should be one hole here. So that electron jumps here, forms a carrier concentration here and a carrier concentration here. So there's an even number of carrier concentration, but here the most of the carrier concentration is dominated by the electrons that is coming from this level. Now, earlier the Fermi level used to be here, now the Fermi level will be in between these two. Okay, because this is the average energy, the electron either here or here, so most of the electrons are coming from here, so Fermi level will be somewhere in the middle. Now, how to calculate the number of electrons or number of charge carrier, because electrons are there dominating charge carriers in n-type semiconductor. So obviously let's find out the number of electrons. So what you do is you first find out how many ions are there. Okay, so that is the number of atoms which left, from which one electron is left and it has gone to the conduction band. So how will you find out? Find out the total number of dopant you have done and total number of neutral atoms are there. If you subtract these two, so that many ionized atoms are there. So each atom is giving one electron, so that many electrons are there. So it's as simple as that. So how do you find out that? You just take the ND and electrons are left. So how many electrons are there in the, what is the probability of electrons in the donor level? If you find out that, so 1 minus EF means this is the left, how many electrons left, or how many electrons are available, you would have written like ED. So this is what electrons available in the donor level, but how many are left? So you just subtract 1 minus, because it's all about probability. So if you substitute the Fermi function that we discussed yesterday, so this is what you will get, ed d this minus this, because minus sign has come because ef is larger, so it will be negative quantity. Okay, so you just rearrange this. Okay, rearrange this. So what you are going to end up is nd e to the power ed minus ef, because 1 plus this value is more. This is like e to the power minus, like it's like 1000 plus 100 plus 1 is nearly equal to 100, you can write. So that concept you can add here, and you just rearrange this one. The minus sign has gone, so this is what you are going to get. Now if you recollect the carrier concentration in the conduction band, the intrinsic carrier concentration, so that is this thing. So number of electron it will tell you, and this is also talks about number of electrons, so these two should be equal. So if you equate them, this is what you are going to get. So you take the nd on the other side, this by nd, this you take to the other side. Okay, and try to solve it. So this is what we are going to do to find the number of electrons. So the logic is very simple. First you try to find out the number of donor atoms which are ionized, and then you equate, because that the number of ionized atom is nothing but the number of electrons are available, and that will be equal to your number of electrons in the intrinsic carrier also. So that is the logic you are going to use. Now same thing as I told you. So nc by nd you do take the ln of, because this is all exponential, so ln if you take, you are getting rid of that exponential. So if you solve this, you will be ending up with ef. Okay, the value for ef. Now take this ef value. It's a simple thing. Okay, you don't need to worry about it. So you just kt, you have taken the kt to the other side, there is this kt is taken to the other side, ef, the 2ef was there, so by 2, so this you have taken to the other side by 2, you are getting the ef value. Just rearrange the whole equation. Okay, nc by nd it was, so it is just reverse it so that the minus sign is taken care of. Okay, now after doing all that, you just replace the nc values here. Now ef, now that is new ef is ed plus ec, exponential ef minus ec. Why do you want to do that is, just a minute, let's go back. If you look at this, okay, if you look at this ef value, you can substitute it here. So this same ef value only. Okay, so exponential ef minus ec by kt, so you will get ef value if you substitute ef by kt minus ec by kt. So ec by kt is remains here, ef by kt is this much, because ef we already have found out. And just rearrange the whole thing. Okay, let me remove this one. Okay, so rearrange the whole thing. So ed minus ec by 2 kt, so this ec comes here, this ec by kt gets cancelled, so by 2 kt, so this becomes by 2 kt. So just rearrange that. Half is nothing but the root over, so ln of root over this thing, ln of root over of this, you just rearrange this thing. Exponential of this into exponential of this is nothing but exponential of this plus this. So when you add them, this is what you are ending up with. Okay, now ef minus ec, so instead of ef, nc value you just substitute here, ef, whatever the ef expression you are getting here, just substitute that. This is what you are going to get for carrier concentration. If you observe carefully, this is ed minus ec now. Okay, ed minus ec, it's not like ev minus ec, and also like t to the power 3 by 2 etas. The dependence on temperature has gone by 1 square root of that, so temperature dependence has fallen down. So earlier case temperature dependence was 3 by 2, here it is 3 by 4, and it also depends on number of dopant. Okay, nd, let me check, So it depends on Nd to Nd to the power. So number of dopant, temperature dependence has decreased, and also it depends on the energy gap between Ec and Ed, and that's the donor level. The same thing you can do with the p-type semiconductor. What you do with the p-type semiconductor is, here the acceptor level is there, so there is a acceptor level, so this is empty level, okay, because it's a trivalent atom. If you add some boron and all, it's a trivalent atom. So what will happen is, electrons from the valency band see this vacant space, they can jump from here. Once the electron comes here, earlier it was a neutral atom, now it accepts one electron, so it becomes negatively charged ion, okay. So here also the Fermi level will lie between this EF, supposed to be somewhere in between this, because this is the available level and this is the full level at absolute zero temperature. The same logic we are going to use here. So what we are going to do here is, how many negatively charged ions are there, that many holes will be created here, isn't it? Electron is leaving from here, it will not be there in the conduction band, but it will be going to this one because it's very close by. So this creates a negatively charged ion, so we call it as acceptor. So Na will represent it, so Na minus. So if you can find out the number of Na minus ions are there, so that many, just a minute, okay, so that many holes are available. So the same logic, Na is equal to Na into FeA. So that is the acceptor level. So now you are calculating how many electrons are there. Earlier you calculate how many electrons left, so that's why 1 minus F, but now you are calculating how many electrons are available in this Ea state. So F of E, that's what it simply, and you substitute the value of this F of E, you will end up with expression like this. Now number of holes, if you calculate it from the previous in the valency band, you get this EF minus EV. So this should be equal to whatever we have found out now, because you are calculating the number of holes only. Equate both of them. So you take this Na this side, this expression this side, so this is what you are getting. Take the exponential, both will be exponential, so take the ln on the both sides. So ln of this equal to ln of E will be, it get cancelled, so this value you are going to get, okay. So now then again simplify it, then E of F you are going to end up with something like this. Now substitute this E of F in this Na experiment, okay. So E of F we are going to get like this, so exponential, just a moment, so E of V and E of A is there, so you're just using that, okay. Let me put it in the full screen, okay. Now you substitute that E of F here and you just simplify that. It's the same logic you are going to use in the case of whatever we have used for the n-type semiconductor. The same simplification if you do, you are going to end up with this equation. So here if you see, the temperature dependence has like 3/4. It depends on how many dopant concentration you have added. It also depends on the energy gap between the valency band and the acceptor band, okay. So that's how the number of P's can be calculated in extrinsic semiconductor. So these two things you just learn and try to learn and practice. When I come back on the Tuesday, we'll discuss a little more about Fermi level and few more problems we'll try to do, okay.